So I'm Jacopo. I'm currently the AI scientist of Coveo. Thanks so much for the organizer of the fantastic meetup and for the people hosting the venue. So the most important news is going to be the first thing that I'm going to say, which is there's going to be pizza. So we're very happy to sponsor that. So that means that I'm actually the person standing between you and food, and I'm very sorry for that. We're going to try to keep it as short as possible, compatible with people actually learning something out of it. Quick introduction of who I am. So I'm the silly one in the picture. I used to be one of the 3 co-founders of Tuzo, which was a startup in San Francisco, Silicon Valley, which got recently acquired by Coveo, which explains why I actually have to use this template, which I really don't like, but unfortunately I actually have to do that. A quick word about the company is going to pay for pizza, which I think is actually nice. Not just the pizza, but the company as well. So this Coveo, we are a multinational group. The company originally is Canadian. We have offices in Quebec City, Montreal, San Francisco, New York, where I actually live. Bassano di Grappa, not really an office, but like Luca is my colleague there. So London and a bunch of other places. We raised $100 million in 2018, and I'm super proud that I actually had yesterday night to change this presentation last minute. If yesterday you happened to walk in Times Square, you would see that NASDAQ actually, as an homage to our company, changed the color of the banner in Times Square. This is the Wall Street Journal. All the major newspapers talk about the fact that Coveo is actually now a unicorn. Not many Canadian unicorns and not many unicorns in general, so actually I have to update it as well. So now we raised $300 million in the last 2 years. So we're very happy and very proud as a company, which means we're actually very happy to pay for pizza, which is not that expensive. So today we're going to talk about symbolic regression and kind of like probabilistic context-free grammars. Anybody familiar with symbolic regression? Awesome. Anybody familiar with context-free grammars? Cool, awesome. So the idea today is actually learning something new about how to mix these two ideas. So we wrote actually a long blog post with code that is shared on GitHub, so it's free. We're going to share later the slides in our Slack and so on. So you're very welcome to go there, go to the GitHub repository, actually play around with the code and so on and so forth. So it's all open, it's all free. If something, there's something that kind of that does not really work, please ping me. I'd be super happy to help you out. The idea about symbolic regression is that we're going to, of course, talk a lot about that. But the idea is that the idea of this tutorial, in general, the blog post and all the code, is not actually to really solve the problem that people usually solve with symbolic regression. So we're actually going to learn something about symbolic regression by doing it in the wrong way. So my strong suggestion is that if you actually want to use symbolic regression in your real life, do not do what we're going to do. This is actually not a joke. Okay. So let's talk about a problem that everybody, and maybe, I don't know, how many here self-identify as data scientists? Okay. So at least some of us, actually have like the entire, our daily life, which is somebody from a business unit or somebody from marketing and somebody from another part of the business come to us and says, hey, I have a problem, I have these 2 variables that I'm interested in this case, let's say revenue and cloud expenditures, whatever that means. And I'm really interested to learn something about these 2 variables, how these 2 variables are correlated, what variables explain what other variables and so on. This is very valuable because if your marketing department or your sales department comes to you and say, I want to understand how much money do we need to spend next year on cloud expenditure, how much money I would expect to get in revenues. So there's a lot of business questions that are actually framed in what is the relationship between variable A and variable B, because that's going to help us make better predictions. So that's a kind of a standard problem that we have. So there are many ways in which we actually solve this problem. The first one is actually we hire people, not very good looking people, by the way. So this is low and costly, as humans are kind of like cool, but they're very expensive, and it takes a long time for humans to actually produce usable code that will explain the variables that we're interested in. Or we can buy business intelligence tools. This is actually a real screenshot from a company in Silicon Valley. It's called ThoughtSpot. It's a very good company. And once you buy ThoughtSpot, which is actually very cool, but what you get is it's basically a set of pre-made models that you can use to tackle different problems. So the way we solve our business challenge is that we get the business challenge from the business and salespeople, and we try to apply one of these models. Unfortunately, this is very rigid and maybe inaccurate because, again, like if you have widely different relationship between variables, it's not guaranteed that one of these pre-made methods will actually work the way it's expected. Also, ThoughtSpot is very expensive. And of course, the way in which we all dream of solving this thing is to hire our private robot army and have our robots work all night and day. We can go on vacation, we can just come back, and they're going to do the analysis for us. So what we're going to try and do today is we're actually going to try and build our private robot army so that we can actually go on vacation and blah, blah, blah. So, of course, this is actually very hard in this generality. This is a quote by a very interesting guy. But the crucial idea here is that we can take some of the ideas from that people use to solve different problems, put them together, and make some nice kind of advances in how to tackle this problem. This is not going to be, again, this is not meant to be like an end-to-end solution that you can actually do. It is meant to be as a stimulating talk and teaching you some new stuff, and then you're very welcome to go out in the real world and actually do that with real tools. So, what's symbolic regression? Symbolic regression is kind of like an automated way to do what we all do as data scientists all day. So when we have a bunch of data points, in an X and Y axis, whatever there is, it's a very, very good best practice for us doing data science to start with something simple and then make it more complex if necessary, right? Everybody here knows the importance, I guess, of baseline models, so we all should start, we all should do logistic regression, and then if really, really, really needed, we should do deep learning. Really not the other way around. So that's a general principle. Once you get this, once you get this problem, the first time we're trying to do is that we're trying to fit the simplest possible model we can think of, right? I know this is a toy example. This does not look like a straight line. We all know that. Just bear with me. So we start with linear regression and say, okay, let's, kind of like draw a straight line and see, how good we're doing to fit this data. And we're doing kind of fine, but not super fine. So what we can do now is that we can decide that this is not good enough, and we can decide that we actually want to do something that's slightly more complex, because this is indeed necessary. So what we do is that we try and categorize the actually as a quadratic expression. It's slightly better as a fit, but as we can still do, we can, there's still a lot of things we can do. So what we do now is that we try and do a more complex model because it's actually needed. And this is a cubic expression that obviously was used to generate this data, so this looks like overfitting, but I swear it's not. So the general idea here is that we start with something simple and we make it as complicated as necessary. These two notions, start with simple, as complicated as necessary, will be the key things that we're going to explore basically the entire talk today. So, symbolic regression is the automated version of what we just did. Instead of doing that manually by looking physically at graph and selecting, more complex model, we start with a family of functions that could fit the data. We measure how well they're doing with some sort of measuring distance. We take the best one, we take the one that we deem are the best one, and we change them to see if we can make them even better. And then we repeat this process, as many times as we deem fit compared to the final outcome we want to achieve. It's very important to highlight that part. So we take the best models and the best function and we change them. Most people actually solve this problem with this optimization technique, which is genetic algorithms, which probably many of you are familiar with. If you're not familiar with this, it's kind of like the algorithmic version of Darwinian evolution. So you have functions, which you kind of can, it's kind of like, mammals in, long time ago. Some of them are better suited than others to live in this environment, and then you randomly change them, random DNA change when two mammals mate. Sorry, I'm very bad at biology, obviously. And then, many generations, after that, you get humans, which are super smart and kind of super cool mammals. That is the same thing you do usually with functions. And this is the right way of doing that. We're not suggesting in any way that you shouldn't do this in the real life. Thanks God, we have so much time on our hand that we can actually try and do something more fun. So what we're going to do today is we're going to do this, and then we're going to solve this problem. Instead of using genetic algorithm, we're going to use it a probabilistic grammar. So we're going to borrow some tools from natural language processing to basically solve the same task. So instead of taking randomly like a huge amount of function, change them slightly and see which one is better. We're gonna actually evolve new function using language tool. All with me so far? Cool. Please interrupt me if something is not clear, because again, the whole point of this is not doing something that works. This does not really work, but is actually to understand something new and that you can use in real life. Okay, now language, which is one of my passions. So, language are actually like Lego bricks. If you never thought about that, you actually should start thinking about that way. So, Lego bricks, everybody familiar with Lego bricks? Yeah. Raise your hand. Oh, finally something everybody knows. Okay, yeah. Next meetup we're gonna do Legos instead of data science. So, you have bricks, which is this atomic part of your toys, this small thing. You have instructions, which is basically like a set of rules that kind of tells you how you combine different kind of Lego bricks. And then you finally have your model, like the lighthouse in that example. This is very powerful. If you're familiar with the distinction between generative and discriminative model, for those of you who are kind of advanced, this kind of looks like a dumbed-down version of a generative model. Like the way you actually combine different things and you go to a final result is the same way in which, for example, if you do, I don't know, knife Bayes for text classification, you actually build your model. The cool thing about this, which I'm just going to say because I think it's important that you know that, but it's completely useless for the rest of the talk, so you can actually not listen to me, is that this thing is invertible. So if you have bricks and you have instruction, you can build models, but then if you have a model that is made like that, you can actually go backwards. So if you have a model, I can ask you the question, which type of bricks and which set of rules combined together produce that model? Is this ability to go from simple to complex and from complex to simple that make generative models so appealing to a lot of things? Sorry, I thought so. Okay, cool. Now back to language. So language are actually exactly like Lego bricks. So we don't have bricks. The bricks of our language are actually usually called words. We have some example here. These are like a very small language. Beast, verb, noun, determiner, adverb, bark, mouse, dog, cat, da, loudly, blah, blah, blah. We have a set of instructions, which we usually call syntax, and tells you, given a symbol of a particular type, how you can get new symbols starting from that. We're going to see an example in a moment, but the idea is that a sentence, S, is built by a noun and a verb. Something that makes sense. A noun is built by an article, like a determiner, and a noun, and so on and so forth. And then, of course, the sentence is the model. So when you combine words with syntax, you actually get sentences. A probabilistic context-free grammar, which is what we're going to use today as our tool of choice to explore this space of function, is basically a way to define a distribution of overall possible sentences in a language. Languages are usually modeled as probabilistic object, and this is one of the formalisms that people usually use to do that. Yeah, I'm going to tell you something later. Okay, so now let's just see practically what does it mean that we actually have a model of language. So we start with a sentence, okay? Remember, a sentence splits in NP and VP, okay? So we start with a sentence that splits in NP and in VP, okay? And then we have a rule saying that we can sample from a distribution saying that the NP, the noun phrase, which is typically something like the dog, the house, or something like that, will actually split either in the dog, like determiner and noun, or just in a noun, with some given probabilities. And here we have another sampling. So a verb phrase can either be a verb or just a verb and an adverb with some probabilities. What we do is that we flip a coin, which is of course biased to reflect this probability, and then we build our tree. So we flip two coins, and the result here is now that we have a noun, and the result here is that we have a verb. Okay? And then we repeat that. How do we do that? We're going back to our syntax, our instruction manual, and then we flip other coins. And we do that until we reach the bottom of this tree. So in this case, we're going to flip two coins. The result is going to be dog, which is word, and barks. Which means that this sentence is actually the sentence dog barks. So this tree is the generative model of the sentence dog barks. Make sense? Remember what I told you before? Which is completely useless for this talk, but it's probably one of the most powerful ideas like in the history of humanity. Okay, now that I have this, if I have a generative model, I can ask the question, given that I observe the sentence dog barks, what is the most likely tree that generated this? This is called parsing. It is one of the hardest challenges in natural language processing, and your mind does it so seamlessly that it actually don't really pay attention to that. But this is very important. So you can go from simple to complex, and then with something complex, you can go from complex to simple. Okay. Again, completely useless, but another example. Sorry. Why did you example? Yeah, sorry. Another example, just to reinforce the point. I have no idea where there are two. But yeah, so sampling stuff. I got a different towing cost this time, so now the noun phrase is going to split in determiner and a noun, and then we're going to get another coin. And then the answer, the result is a cat meows, which means, again, the sentence is cat meows, and then again, you can think of it as a process going from simple to complex, and you can always go from complex to simple. And that's it. All good with grammars? Cool. Now, the crucial observation of today is that actually mathematics is a language. I know it's not exactly surprising. But yeah, so we can think of, the family of polynomials, the polynomials that we actually try and use to fit our data. We can actually think our expression as part of a language with, some primitives, some words, and so on. Mathematics doesn't have the language of dog or cat, but have the language of, exponential, or as the language of variables, as the language of multiplication, and so on and so forth. So if I build a grammar for this language, instead for the language of, a dog, a cat, and so on, we can actually think of the polynomial expressor as the sentences in this abstract language. Of course, once you have the grammar, we can sample from it. Sample from the grammar means, again, we start with something, and in each of these steps in this tree, we flip a coin, and then we decide what to do. Okay, that's been sampled. Okay, so now we have a formula. We have, here we sample an integer, so any number between 0 and 10, and here we sample an operation, say addition or multiplication. We flip our coins, and the result in this case is 3 times x. So we have a number, we have an operator, and we have a variable here, which is the equivalent of this sentence, y equals 3 times x. And you can think of sampling from this grammar once you build one and get all sorts of expressions. This is a screenshot from a web page that's public. You can run all the example in your browser. The code is available on GitHub. So if you want to try that out, you can actually see that this works. So this works. The entire thing does not work, but this works. So you can actually go online and try that yourself. Every time you press run, you're gonna get obviously different formulas. The formulas here are expressed in this idiotic way with a lot of parentheses, but if you can actually map this to the very familiar function that you can see here, you can see that our simple grammar can generate a lot of random expression. Okay, some of this very, very, very simple, some of this very complex. Okay, so now we have expression. Remember, one of our problems is that we need to generate enough functions to try down on your data so that we can actually assess which one are good and which one are not. So now is the second part, how do we assess which of these functions are actually good? So how do we go, if you remember our manual example, how do we decide that the linear fit is not good enough and the cubic fit is actually good? How do we do that automatically? We're gonna assume, we're gonna make like a standard but also kind of disappointing assumption, which is that all the value are actually, each data point is actually normally distributed around the true value, so there's kind of a general Gaussian noise around all the points, which means that we can basically treat all these examples as standard polynomial regression. If you psych it to do linear regression, polynomial regression, this is kind of equivalent to basically least square method and stuff like that, which again, it's just for convenience. You can think of this as a swappable part of the entire mechanism, so for different functions and different use cases, if you have more nuanced or more complicated version of this criterion, you can actually use that and everything will work as well. So this is a decision just made in the, for the sake of simplicity and for the sake of actually encoding your browser that runs reasonably enough. Okay, so let me see. Okay, so these are 3 examples that has been generated. So this is the true value. So this is actually like what generated with some Gaussian noise. You can see this is clearly a straight line. Okay, it's a noise, and you can see this is clearly like an exponential. So when we do this, what happens? So when we try and measure how good our constant function is in mapping this thing, we see that the system says that it's overwhelmingly likely that the best fit is the constant function, okay, instead of the exponential one. And you can see that we can actually get an estimate around the real parameter value that generate the function there. If you're gonna go back here, you see that this is the function, so y is basically equal to 4, okay? Which means that the system is very, like, can understand that this is the best function, and it can actually also tell us that the vast majority of, so the probability of the true value being 4 is actually very high, which is correct because we generate that, so we know that. You can try and do the same with the exponential function, and you can see that the system is slightly more undecided here about the tree function, but still the overwhelming majority of what the system believes is around the exponential function. And if you go here again, you can see the traces of MCMC, which basically tells you that the true parameter value is actually around 2, which is this number here, right? Again, we put this function by hand just to make sure that the criterion that we use to find out which one is the best function actually works. Okay, and it seems to work. I think this is a reasonable assumption. So we had, our problem is we need to we have x and data on x and y, and we don't know what is the relations between x and y, and we want to generate a lot of functions that may explain this relationship, and we want to have a way to evaluate those functions. So the generation of the function, which is part 1, is going to be done with the language. We're going to generate them like we generate a dog barks and a cat meows, okay? And the accuracy, so measuring how good functions are just going to be done just like we did today with this normality assumption. We're just going to basically try and understand how good is the function fitting, how good the function is fitting the data, and so on and so forth. Okay, so now that we have these two parts, we actually can combine them together and actually build what we want to build. So, the key intuition here, we did it before. We start with a simple hypothesis and we make it more complex only if that is necessary. Okay? So, first, we pick like a sentence from our grammar, mathematical expression. Simple expression are more likely to generate, now we're going to talk about that, and then we test for data fitting with our mathematical assumption. And we're going to repeat that until we're kind of there. Okay? Make it more complex if necessary means that we should strive, again, we should start with simpler thing and then go on to more complex thing only if it's needed. Okay? So which is important that our grammar generates more, given like a distribution of sentences, it's very important that our grammar generates simpler stuff more than complex stuff, right? Because we want to make sure that we don't evaluate complex expression if it's unnecessary. All on board about that? It's the same idea of like, we should start with logistic regression and go to deep learning, a month later if that doesn't work. Okay, this is the automated version of that. So, I'm claiming, and I'm going to ask you why, but I claim that in our grammar, simple expressions are more likely to be generated. So that the grammar that you actually build has actually this simplistic criteria, you may think of Occam razor, that's actually built in. And I know that's actually true. But the question is, I want to know, does anybody have any idea or want to try to reason with me why this is the case? Because this is clearly important. Because if you have a grammar, think of like generating a sentence. If you have a sentence generator that only generates paragraph, like in, like very, very long paragraph, it doesn't really work for something like that, right? Because we want to generate stuff, like simple stuff first and then go to longer things. So this is very important and we can claim that. Anybody has any idea why this is the case? Anyone wants to try? Okay. Sorry about this epilepsy. 1 second. So, every time we make a choice, let's go back to language. I feel that these two things are actually the same. So, every time I make a choice on how to expand a node of this graph, I need to, flip my coin. At some point, if I flip a coin, and so on and so forth, and then I get to this sentence. The shorter the sentence, typically, the less choices I need to make to produce the sentence. Which means that even that all these flips are randomly and independently generated, which means that, you know, shorter sentences are much more likely to get generated instead of longer one. If you think of generating a sentence of coin toss, when you have, I don't know, 80%, I have 80% of probability of getting tail, and, you know, 20% of getting head, and then if I get tail, I continue, and if I get head, I actually stop. We'll see that the vast majority of things will actually be very short, right? Why? Because, you know, every time I flip the coin, you know, I have like a 20% probability of actually stopping, you know, which in independently distributed trial, this is actually sum up very quickly to be almost certain that the sentence is gonna end. This is kind of the same intuition. Since we're kind of built in this idea of building a tree one step at a time, the less probabilistic choices are needed, you know, the easiest is actually the final sentence that gets generated. So that's why we kind of cheated, or somebody would say that's kind of a very clever trick, depending on, you know, who you ask. If you ask me, it's a very clever trick, because I did it. So this idea is actually kind of like the equivalent of the Occam reason, right? Again, if you want to try, when you go online and use the browser, you can actually manually try and switch all the probabilities and see at which condition is actually true and which condition is actually stopping. Sorry again for this. Okay, back to our, so, all on board with the general plan. So this is real data points with real, this is the truth. So again, we manually build that, so we know the truth. So this is what generated this graph, okay? So the question now we have is all the system that we built together, like the probabilistic grammar to get expression, and then the normality assumption that we have. How well are they doing at actually approximating the actual truth? And when you run this, you actually find out that it's kind of okay. So I would say this is a reasonable approximation. This is a reasonable approximation. And then, you know, there's a bunch of things that are actually, you know, some of them are actually okay, some of them are actually, you know, maybe not super okay. But the whole idea is that for very simple polynomials, even a simple probabilistic grammar and the normality assumption will actually work very well in understanding what is the relationship. If you go back to your marketing person, going to you and handing you this graph and saying, can you please help me explain this graph? What you have now, if you have like a principal way of actually exploring the space of all the polynomial expressions that may explain the graph, which are infinite, of course, and you're actually going to stop at something that kind of makes some sense. The other thing that we want to just say is that since we're fitting arbitrary x and y data points, but we're fitting them with polynomials, the nice thing about polynomials is that they give you an explicit model about the relationship between the two variables. I think many of you are familiar with a lot of problems the AI community have these days with interpretability, explainability, black smoke models, unfairness, and so on. So one cool thing about kind of focusing your effort on full interpreter model is that, you know, you actually have equations. So, I mean, I would say that most people can actually read this without English, but even if you cannot read this for whatever reason, maybe because you're a marketing person, then we can still translate that automatically to like an English sentence. Again, you can try that out in your browser. So for example, when you have this, it's very easy to build a bunch of rules that will transform whatever things comes out of the model and tell you, for example, that according to the model that we found, an increase of $1 million, whatever, in cloud expenditure would lead to an increase of 4 in revenues. Which means that the marketing person handed you this, okay, and say, explain this to me. What happens if I spend, you know, twice as much in cloud next year? And then what you get out of it is this, but nobody understands this, but you can go from this to a fully English or Italian or whatever you like explanation of this thing very, very, very quickly. Again, this is an hack, but if you want to try it out in your browser, it actually works. And again, if you can imagine, these are very big space, like the space of polynomial expression is obviously very big, but the point is, you can totally imagine writing a parser for this expression that translates every single expression into an explanation in English that makes sense. It's actually fairly easy to do. So, So where to go next? Again, I think we went from 0 to like symbolic regression to symbolic regression, context-free grammars, putting them together, trying and solve the problem that we actually in the first place, which probably by the time we solved it, we kind of all forgot what the problem was, which is kind of useful. But then the question is this actually useful in real life? What can you do with this type of technique? What can you do when you're actually a real marketing person, your real job, in your, like in the office, and you're required to actually produce some actionable output? There's a bunch of things we would like to explore and do more and do better, which I think I suggest you to explore, do more, and do better. So the first thing is that probabilistic programming languages are very cool. All this tutorial and the GitHub repo and the blog post has been written in WebPeople. WebPeople is a JavaScript-based language, and I swear to God, I never thought in my life I would say good things about JavaScript. But it's actually very cool. It lets you start with basically your browser, and it lets you explore a bunch of stuff, a bunch of ideas, especially about probabilistic programming languages. If you like to model things in a generative way, like we discussed before, probabilistic languages are very, very, very useful because they let you encode with the language that you know, Python, or God forbid JavaScript, your assumptions, and then you push down to the compiler all the problem about inference. Remember the problem going from the tree to the sentence and then back from the sentence to the tree? Like, a problem that people usually have is that solving that in generality is actually very, very hard. But solving that for specific cases is actually okay. And probabilistic programming language lets you just explain the model. So you give them the tree and the model to generate the sentence. You give them the sentence and they will actually do the inference for you. So you don't have to take care of the fact that it's actually very hard to do this back and forth. Which is great because it means that you can focus on modeling your problem instead of doing very, very complex probabilistic inference. The new kid in town, so the coolest kid in town is now called Pyro, which is Python, thanks God. But Pyro actually sucks, it's full of bugs. It's very new, it's backed by Uber. There's a Italian guy that works there, which is super nice. So I suggest you also to try that, not just because he's Italian. And then other thing that I really, really suggest, we were discussing that before. This book is called Probs Mods, which is the short version of Probabilistic Models of Cognition. It's a textbook online. It's completely free, open source. Everything is on GitHub, and it's an interactive textbook. So it's a textbook that explains you how to use probabilistic inference, especially applied to cognition. So especially applied to phenomena that actually humans are very good at and machines still kind of suck at. But it's all interactive because it's used by people. So you can try, it's very good because when they explain you something about inference, you can actually try that in your browser and you can change the code and see how they change. It's very good. It's done by, it's maintained by Joshua Tenenbaum and Noah Goodman. Joshua Tenenbaum is the head of brain and cognitive science at MIT. He won the MacArthur Prize like 2 months ago. He's one of the leading figure in actually computational models of humans. Noah Goodman is a psychologist at Stanford. He also worked for Uber. He's one of the guys behind Python. Two super smart guys, so I strongly suggest you to read everything they say. On the general robo-scientist thing, we are very lazy people, we want robots to work for us and we want to go on vacation kind of thing. Surprisingly enough, I'm not the first one to thought about that. So there's actually been a fair amount of work, maybe 10 years ago. This guy, Garamani, somebody knows Garamani? No. Garamani was the co-founder of a startup called Geometric Intelligence, which was bought out by Uber, and now it's called Uber AI Labs, like a bunch of years ago. And it's like one of the world experts on Bayesian inference. But he used to work with his Cambridge group on this problem of, he was calling automated statistician, because back then data science wasn't really like a cool thing. So automated statistician is the uncool version of robot data scientist. And so there's a bunch of paper written in the generative Bayesian kind of thing that Garamani did. Garamani is a much less funny guy than Joshua Tenenbaum, but still is cool. A very, very, very new work by the MIT group is composing kernel-induced processes, which is philosophically the most similar thing to the one we actually built today. I mean, this is a real thing. Like this is like 40 pages of math. This is a real thing. But the point is, philosophically, this is very, very similar to what we did. They're not using symbolic regression as a way of generating function and explain data. They use this thing called Gaussian processes, which are cool in their own way. So if you don't know what they are, I strongly suggest you to look for that. But they use the same idea that Gaussian processes are a language. So you can actually have a language that describes these processes, and you can actually treat them as a grammar, and then you can evolve new processes, and then you can see which one fits the prediction best. Finally, if you're really interested in kind of doing symbolic regression in the right way, like tried and tested, and way everybody does that, nobody's gonna fire you for that, and so on. It's gonna be the standard genetic algorithm approach that we kind of described. There's a very, very cool library. It's called GPLearn. It's a library written in Python. There's a lot of examples, which I strongly suggest you to see. Finally, a quote from a guy. Finally, a serious quote after all these stupid ones. It's one of my favorite quotes by Alan Turing, which kind of invented this whole thing. By all, I mean kind of old thing. We can only see a short distance ahead, but we can see plenty there that needs to be done. As I always like to say, let's not forget, it's up to us to get it done. Thanks so much, guys.